Good evening, sir.
Good evening, madam.
Shall we start, sir? They'll be joining slowly.
Yeah.
Yes, sir. So today what we are going to see? Today our topic is
Our
non-parametric.
top. No.
Ah,
Today our topic, because there is some important work for Parag sir. So today's session
it's
will be
Monday.
after tomorrow, and today I'm going to talk on chi-square test of goodness of fit.
Okay. Okay.
Okay.
Okay, sir. So good evening to everyone. We are assembled here for doing online international workshop on Jamovi. Here our resource person, Dr. Chaudhary sir is here. As mentioned here, Sir Chaudhary sir is Associate Professor of Statistics in MG Science Institute, Ahmedabad, Gujarat. Welcome you, sir. So today, sir is going to handle the session on chi-square test of association and goodness of fit. Welcome you, sir. Thank you, sir.
Thank you. Thank you. Okay. Good evening, all. So today's topic is chi-square test of association and goodness of fit. So just a minute. Okay, so actually, according to the schedule, today's topic was non-parametric test. So because of some important work, we have rescheduled, interchange the topics. So today we will discuss about the chi-square test of association and goodness of fit using Jamovi. So now you are familiar with hypothesis testing. So in yesterday's session, Parag sir explained you about the hypothesis and the types of hypothesis, then how to set up the hypothesis, and I think Parag sir explained you about the one sample t-test and some non-parametric test. So basically, in hypothesis testing, we have different type of test. But again, it depends upon the type of data as well as it depends upon the nature of the data, nature of the distribution, right? So when we have a normal distribution, that means if data follows a normal distribution or data is coming from a normally distributed population, then we have some parametric test. If the data does not follow, or if the data is not coming from a normally distributed population, then we have some non-parametric test, right? So basically t-test is used when we have a numerical variable. A variable is of continuous type, right? Then we go for a t-test depending upon the nature, whether it is normal or non-normal, right? So as you know that there are two types of variable. One is a qualitative, another is a quantitative. So for quantitative, we have different tests, but when we have qualitative data, so in most of the cases, we use a chi-square test of association, which is also known as chi-square test of independence, and another one that is chi-square test of goodness of fit, right? So we will discuss one by one. So before we go to the chi-square test, right? So we have the proportion test. So when we have a qualitative data and the variable of interest is classified into only two categories, so that type of data is known as a binary data. And in that case, if we are interested in testing the proportions, then we go for the proportion for the two outcomes, right? Similarly, we have multiple proportions. If there are more than two categories, more than two levels of the qualitative a variable, then we go for a proportion test, that is multiple proportion test. Then the next is, many times what we have, we collect the data from some population, or we have some data, sample data, and we want to test whether that data is coming from a population with some specific distribution. Say, for example, whether data is coming from a normally distributed population, or whether it is coming from a binomially distributed population, or whether it is coming from a uniform distribution. In that case, we can go for a chi-square test of goodness of fit. So you will get idea about all these tests using different examples, and we will do that in Jamovi. So another one is a chi-square test, which is also known as a Pearson's chi-square test of association, or a Pearson chi-square test of independence. So we know that we have, when we have two numerical variable, then we try to find out the correlation between them. If we have two numerical variables and someone is interested in finding whether the two variables are related or not, so we find out the correlation, that is known as a Pearson correlation coefficient. So that is for the numerical type data, quantitative data. Now, what happens when we have a qualitative data? We have two qualitative variables, right? We have two different qualitative variables. Say, for example, we have gender, male, female, and we have the class obtained by the corresponding respondent. So we want to know whether the class or grade obtained by the respondent depends upon gender or not. That means both the variable, gender as well as the grade, both are qualitative variable. So in that case, it is not possible to compute the correlation, but the corresponding the corresponding word for the relationship is association in case of a qualitative data. So this Pearson chi-square test is used to test whether the two qualitative variables are associated or not. For that, we can use the Pearson chi-square test, right? So there are some different measures of association for nominal type data as well as for ordinal type data. So that also we will discuss in today's session using Jamovi, right? So first of all, the proportion test. Now suppose I have the data about the shopping preference, right? So obviously there are two choices, two options, two levels. The preference may be online or it may be offline, right? So the variable of interest is shopping preference, which has two levels, online and offline. And at the same time, the same individual, 250 individuals, are classified with respect to their gender, that is male and female. So in this case, we have two variables, both are qualitative. One is shopping preference, which has two levels, online, offline. Another is gender, which has two levels, male and female, right? And for such a 250 individuals, we have collected the data on both the variables, right? And based on this sample data, researcher wants to test certain hypotheses, right? So here the researcher claim that majority of the respondent prefer online shopping, right? Majority of the respondent. So actually we have 250 respondent. So out of 250 respondent, researcher claim that majority of the respondent prefer online shopping, right? And obviously in this case, when we talk about a qualitative variable, always we use proportion as a measure. In case of a quantitative variable, either we can use measure of central tendency or we can use standard deviation, right? And depending upon the research inquiry, either we can test about the average or we can test about the variance. So in this case, the variable of interest is qualitative, and in case of the qualitative, we can go for the proportion. So here the variable of interest is shopping preference, which has two level, online and offline. So the data is stored in shopping data.sav. So remember, intentionally I have taken the SPSS data file, right? So in the earlier cases, we have used the Excel data file or a CSV data file. So in Jamovi, we can import SPSS data file also, right? So that is why I have prepared the data in SPSS and we import that data. So we can import SPSS data file in Jamovi also, right? Now, from this particular problem, we want to set up the hypothesis, right? So what is the question here? Researcher, the claim of the researcher, majority of the respondent prefer online shopping, right? So if we talk about online shopping, so proportion of respondent who prefer online and proportion of respondent who prefer offline. If online is a success, then we call it as a P, that is proportion of respondent who prefer online. And since then there are only two levels, so the complementary of online, that is offline, so it is 1 minus P, right? So out of 250 individuals, we count how many prefer online shopping, right? Say for a simplicity, 100 prefer online shopping. So the proportion, sample proportion of respondent who prefer online, that is 100 divided by 250. And the complementary, that is 1 minus 100 divided by 250, that is the proportion of the respondent who prefer offline shopping, right? Now, since the question is majority of the respondent, as we know that proportion or probability, the value of the proportion or probability always lies between 0 and 1. Okay, so if the proportion of success is 0.5, so proportion of failure is also 0.5 because they are complementary of each other, right? Similarly, in this case, proportion of, suppose assume that the proportions are equal. So when we say they are equal, so P equal to 0.5 for online and Q equal to 1 minus P 0.5, that is for offline. Okay, but the question is majority of the respondent prefer online shopping, right? So in this case, what we can do, either it is equal to 0.5 or more than 0.5, right? So so before we set up the hypothesis, let us look at the data which is in SPSS format, right? So in this case, I have ID, then gender, and then shopping preference. So both the variables are both the variables are nominal variables, and we have coded them as one for male and two for female, one for online, two for offline. So this is the data view in SPSS and variable view in SPSS, right? Now what we have to do, we have to open this data in Jamovi, right? So let us see how to import. Now you know, you are familiar with opening the data in Jamovi. So it is simply go to the menu, sorry, go to the menu and open and go to your desired location where the file is stored. So this is my shopping data, right? So just select that file. It is actually SPSS data file. So click on open and it will open your data file, right? So you can see there are 250 respondent, right? There are 250 respondent and two variables. If you click on the gender variable, we can see that male equal to 1, female equal to 2, that is the labels, or what we call it as the labels. Okay, and it is a nominal variable. Second variable, that is shopping preference, which is also nominal, and online and offline. So this is what we have the data, right? Then the next part is we have to set up the hypothesis, right? Since P denote the proportion of the respondent who prefer online shopping. So according to the research question, we can set up the hypothesis that majority of the respondent. So P greater than 0.5. Okay. So according to the claim, what is the claim? The claim is majority of the respondent prefer online shopping. So it is possible when P is greater than 0.5, right? So proportion of the respondent who prefer online, that is greater than 0.5. Now, this is the statement, the claim, right? Now, what is the complementary of P greater than 0.5? So, the complementary of P greater than 0.5, that is P less or equal to 0.5, right? And out of the two, one in which equality sign is there, that is considered as a null hypothesis, and the other one, that is the alternative hypothesis, right? So this is how we can set up the hypothesis testing problem, right? So P is a proportion, right? Majority prefer online, so P greater than 0.5. Its complementary is P less or equal to 0.5, and the one in which equality is there, that is taken as a null hypothesis. So other one, that is the alternative hypothesis, right? So this is what is the procedure to set up the null and alternative hypothesis, right? Now, once we have set up the null and alternative hypothesis, since the problem is about the proportion, right? So we can use here the binomial test, or you can write the same statement in terms of the in words also. So majority of the respondents do not prefer online shopping, and complementary against majority of the respondent prefer online shopping, right? Now, to do this in Jamovi, we have a simple technique. Now, see, the first part is the exploration in the analysis menu. Second part is t-test, in which we have one sample t-test, independent sample t-test, pair t-test. Along with this, it consists of non-parametric test also. Okay, so there is no separate non-parametric test menu in Jamovi. Just like in SPSS, we have a separate menu for the non-parametric test. But in Jamovi, it comes under the same. So, say for example, if we apply one sample, so if the data is not normal, automatically we can select the corresponding non-parametric test in the respective menu. Okay. Similarly, the second part is the analysis of variance. So here also, look at this. So all these are the parametric test. Okay. One way ANOVA, repeated measure, ENCOVA, MENCOVA, right? And the corresponding non-parametric tests are here, right? Next one is the regression, and then we have the frequency, right? So as you know that frequencies are basically used when we have qualitative data, either nominal or ordinal type data, right? So this is the first one sample proportion test, having two outcomes, right? Or having n outcomes, right? So first one, that is a binomial test for the qualitative data, right? So this test we have to select for our problem. Why for binomial test? Because there are only two outcomes, online and offline. So we go for, and we want to test the proportion. So we go for a binomial test. Okay. So this is how we can select the binomial test, okay, from the frequencies menu, and then you have to select. So click on that, right? And then we can see that here it shows proportion test, right? It shows the proportion test. As soon as you select that menu, that option from the menu, in the result section, in the output section, you will always get a blank table. Once you select the variable, it will calculate the results and put it in the table. Okay. So this is, in this case, our hypothesis problem is about the shopping preference. So we select the shopping preference and put it in the variable section, right? And accordingly, we have the output shopping preference online. How many total? 130 out of 250. Offline 120 out of 250, and this is the sample proportion. Okay, this 0.52, that is 130 divided by 250, that is a sample proportion, right? And this is the sample proportion 0.52. Okay, and this is the estimated that this is a p value. Okay, so let us see again. Once you select this, then we have some additional options. So in our case, what is the null hypothesis? P less or equal to 0.5. Alternative is P greater than 0.5. So depending upon the situation, you have to set up the hypothesis. So your alternative hypothesis may be one-sided, that is left-sided, or it may be right-sided, or it may be two-sided, that is two-tailed, right? In this case, P greater than 0.5. So it is the right-tailed test, right? So here we have the option whether the test value is not equal to or greater than or less than. In our case, the test value, actually the general hypothesis is P equal to P0 against P not equal to P0 or less than P0 or greater than P0, where P0 is the specified value, right? In our case, this 0.5 is the value of P0, that is known as the test value. So that is why here we have the test value. Okay, this is the test value. If your test value is different than 0.5, you can change that value here. Suppose I want to test the hypothesis that the proportion of the respondent who prefer online shopping is greater than 0.8. So in that case, here I have 0.8 and here I have 0.8. So depending upon the hypothesis, you have to set up the, depending upon the research question, you have to set up the hypothesis, right? So here it is 0.5. By default, it is 0.5, but depending upon the problem, you can change that value. Okay. Now, the next part is the alternative hypothesis. My alternative, that is test value, P greater than 0.5. So I can select the second option, P greater than 0.5. Test value, P greater than test value. Test value is 0.5, right? So once you select that, so look at this. See, just focus on the P value, this last column. When I change it to not equal to, the P value will be different. When I change it to greater than, the P value will be different. When I change it to less than, the P values will be changed, right? So P value depends on the type of alternative hypothesis, right? So, and if you want the confidence interval, you can select the confidence interval so that in your output you can see the confidence band also, 95% lower limit and upper confidence limit, that you can see here. You can change that to any number, right? So generally we use 95% confidence interval or we use 99% confidence interval, right? So this is how we can use the binomial test, right? And whatever the output we get, right? So this is the output and this is the p value for our hypothesis testing problem, right? The first one, because we are interested in online shopping preference, so the corresponding p value is 0.28465, right? And depending upon the p value, you have to take the decision about whether to reject the null hypothesis or whether we fail to reject the null hypothesis, right? So here this is the observed value, p cap, right? X upon n, 130 upon 250. So this is the observed value, right? The p value of the test is 0.28465, which is not less than 5%. So we fail to reject the null hypothesis, right? So that means there is no sufficient evidence to support the claim that the majority of the respondents prefer online shopping. We fail to reject the null hypothesis. That means, in other word, we can say that the null hypothesis is accepted, right? So this is how we can use the uh, proportion test for two outcomes, which is also known as a binomial test, right? Which is also known as a binomial test. Now the next is multiple proportion test, right? Now if your variable, qualitative variable, is classified into more than two categories, right? Say for example, we have the data about gender. We have collected the data, right? And in that case, we have some respondents are male, some respondents are female, some respondents are transgender. So in that case, we have more than two labels for gender variable. So in that case, we can go for multiple proportion, right? So anytime when the variable has more than two labels, qualitative variable has more than two labels, we can go for the multiple proportion test, right? Now to understand multiple proportion test, I have taken a very simple example. So a teacher figures out that the final grade in statistic department are distributed as this proportion, right? So A grade, 25% of the students secured A grade, 25% B grade, 40% C grade, 5% D grade, and 5% E grade, right? So this is what the teachers believe, right? Now at the end of a randomly selected semester, the following number of grades were recorded, right? At the randomly selected semester, this is the grade distribution. So A grade, out of the total student, 36 got A grade, 42 B grade, 60 C grade, 14 D grade, and E grade, 8 students, right? Now, what is the question here? The question is, if the grade distribution for the department is different than expected, right? Now, what is the expected? So, this is the expected grade, okay? What is the expected grade? So, this is the expected grade, okay? So, look at this. This is the expected grade, okay? This is the expected grade, okay? And this is the actual data observed at the end of the semester. Now we want to check whether the grade distribution for this particular department is different than expected or whether it is same as expected, right? Now, and we want to test at 1% level of significance, right? Now, to set up the hypothesis, so actually in earlier case, we have only two outcomes, out online and offline. So we have P and Q as a proportion. In this case, we have the proportion P1, proportion of students securing A grade, P2, proportion of students securing B grade, and so on, right? So, and this is the expected grade, right? This is the expected grade. So we can set up the null hypothesis as PA is 0.5, that means proportion of the students securing A grade is 25%, right? It is based upon the expected data. This is the data, okay? So it is 0.25, PB 0.25, PC 0.40, PD 0.05, and PE, actually it is E, right? So PE, that is 0.05. That means the distribution of the grade for the department. This is the data for the department, okay? So this is the data for the department. So for this department, the distribution of grade is same as expected. Against, it is different than expected. That means the proportion is not in this manner. Okay. So this is how we set up the hypothesis in terms of the multiple proportion. Right. Now, what is the test? In this case, the test is chi-square test, right? It is a chi-square test of multiple proportion, right? Now, the formula is very simple. This is just for your reference, right? So it is summation of OI minus EI whole square upon EI. So what are these notations? This OI is the observed frequency. In our case, this 36 is the observed frequency for A grade. 42 is the observed frequency for B grade, and so on, right? And EI, that is the expected frequency. Okay, that is expected, right? So in this case, this is the formula. So we calculate for each grade this value and then sum, and you will get a chi-square test statistic value. And it follows a chi-square distribution with k minus 1 degrees of freedom, right? So this k is the number of groups. Say for example, in our case, A, B, C, D, E. So 1, 2, 3, 4, 5. So I have 5 levels for the grade. Okay, there are 5 categories for the grade. So my k equal to 5. So 5 minus 1, that is 4, is the degrees of freedom for the chi-square test, right? Now the expected frequency can be computed as this, right? So actually pi is the proportion under the null hypothesis, say 0.25, right? But in our data, we have total number of students. If we sum all these observed data, so that gives you the total number of student, total number of respondent, that is capital N. So that N multiplied by this pi, P1, then P2, and so on. So that gives you the expected frequency for the corresponding cell. Okay. So this is under the null hypothesis, right? Now to do this, we have a way. So now see, this is again very interesting because I have the data. Look at the data. This is my data. So actually this data is a summarized data. Okay, this data is a summarized data. Actually, for the total number of students, I have counted how many secured A grade, how many secure B grade. So it is a frequency table, right? But if we have a raw data, right? If we have a raw data, then in that case, we have a column, okay? But in this case, we don't have a raw data, we have a count data, okay? So in Jamovi, we can also directly use a count data for the hypothesis testing. How we can do that? So look at this. So we can create a similar table, right? So first column is a grade, that is the label categories. I have 5 grades. Second column is a count. That means the frequency, right? So the frequency of A is 36, B is 42, C is 60, and so on. Okay. So once we have prepared this table, so Jamovi will consider it as a raw data, right? So so 36 times we have A, 42 times we have B, and so on, right? So once we have this type of table, right, because it is so what we call it as a summarized data, right? So for summarized data, we can use this technique. But if we don't have a summarized data, we have a raw data, so we can enter the data in Excel file, right? Or directly in Jamovi, say grade obtained by the student individual, right? Serial number, that means, or say for example, seat number and the grade, right? And then we can apply the chi-square test of goodness of fit or for the n outcomes from the frequency option, right? So in this case, say for example, let us go to the Jamovi and how to do this, right? So see, just create a new data file, right? And just change this variable to say, for example, it is my grade, right? And it is a nominal variable, and you can use the label as A, B, C, D, and E, right? And the second variable, we can call it as a count. Now, this is the procedure when we have a summarized data. Okay, we have a summarized data. Say, for example, in our example, it is 36, 42, 60, 14, and 8, right? So it is 36, 42, then we have 60, 14, and 8, right? 60, 14, and 8. Okay, then we have 8. Okay, so this is my data, And then simply we have already prepared this. You can remove this column. That column is not required, right? So this is my data, right? Now go to frequency, go to n outcomes, right? Now see, in this case, there are two options. Now this is again very interesting and very important. If you are using a raw data, okay, if you are using a raw data, then directly we can use the variable. Okay. Say for example, I have entered the data as a grade, A grade, B grade, A grade, B grade, C grade, like that. So whatever the number of student I have, so that many rows I can enter grades. Okay. So in that case, you can use directly the variable and Jamovi will compute the frequency for that. But in this case, I have count. That is why here it is mentioned optional. Okay. If you are using a summarized data, you can use this count technique. So my variable is grade. Okay. And then now see, count by default, it is taken as 1 because Jamovi is assuming that you are using a raw data because I have not entered anything in the count section. So that is why it is taking count A equal to 1, B appears one time, C appears one time, like that. But since I have a summarized data, so I can enter this count in the count optional. And accordingly, see, this is your actual table, right? The labels, that means the grades, their corresponding frequencies and their corresponding proportion, right? So out of the total respondent, the proportion of the respondent who secure A grade, that is 22.50% of the respondents secure A grade. Okay, so this is that table. Okay, now once we have this, right, according to our technique, what we want observed frequencies, we want expected frequencies, right? So if you look at the table, so this is the observed frequency, count is the observed frequency, so expected is not there. Okay, so what you can do, you can add the expected frequencies, right? So here you can add the expected frequencies. In the right hand side, we have the checkbox, so that add the expected frequency, right? So it will compute the expected frequency. How the expected frequency can be computed? So that is n multiplied by pi, n multiplied by the corresponding pi. So it will compute the total number, total respondent, right? And then for each, it will multiply by pi. So this is the proportion, right? So that gives you the corresponding expected frequency. And accordingly, we have the expected proportion also. Okay. So this is how we get, right? But in this case, actually what we have, so since we are not testing the equality of the proportion, okay, we are not testing the equality of the proportion. If you look at the expected frequency table, so here always for all we get expected frequency 32, 32, 32, 32 and 32. Why? Because by default it is assuming that all the grades are having equal proportion. So under that assumption, it gives you expected frequency 32, 32 and 32, right? But that is not the case. So for to change that, what we need to do, we need to click on the expected proportions, right? And here we have to change the ratio, right? So what is the ratio we have? According to the table, what is the expected, right? So look at this. What is the expected? The expected is 25%, 25%, 40%, 5% and 5%. So what we can do, we can change this ratio. We can change this ratio to here. It is say 25, right? This is also 25 and then we have 40%. Then we have 5% and 5%. Now see, all the expected frequencies will be changed. Okay. So this is 40, this is 40, this is 64, this is 8, and this is 8. Right. So accordingly, it will change the expected frequencies. Right. So these are the proportions, right? These are the proportion which we are testing under the null hypothesis. So this is my null hypothesis, 0.25, 0.25, 0.40, 0.05, and so on. So look at this. So these are the proportions, right? And for this, we have the chi-square test. So using this formula, we get the chi-square value as 5.25, right? And there are 5 levels. So the degrees of freedom is 1 less, that is 4, and the corresponding p-value, that is 0.26259. Okay, so that is the p-value. Now, since the p-value of the test, right? If you compare the p-value, so p-value of the test is not less than 5%, right? Look at this. The p-value is not less than 5% at 1% level or 1% because we are testing at 1%. So it is greater than 0.001. We fail to reject the null hypothesis. It means there is no sufficient evidence to support the claim that the grades are different than expected, right? Because our claim is test whether the grades are different than expected. So there is no sufficient evidence to support the claim that the grades are different than expected, right? So this is how we can test the multiple proportion, which is also considered as a chi-square test of goodness of fit, right? So that we will discuss in this part. Okay, now suppose this is another example. In this case, what we have, a doctor believe that the number of births by season is uniformly distributed, right? So to take, this is the claim of the doctor, this is the belief of the doctor that the births are uniformly distributed throughout the season, right? To test this claim, suppose researchers selected 2246 births and record the season in which each take place, right? And accordingly, we have a table, right? So this is the table, right? Now, at 1% level of significance, can you reject the claim that the distribution is uniform? So this is the claim, okay? This is the claim, right? That the number of birth by season is uniform. Whether we call it as number of birth or whether we call it as a proportion of birth by season. So there are 4 seasons: spring, summer, winter, and fall, right? And the total number of birth, 2246, they are classified according to season, right? So this is that table, right? Now, what we want to test here. So we know the uniform distribution. Uniform distribution means the value, the probability is uniform throughout that interval. Say I am taking the interval 0 to 1, right? So within the interval 0 to 1, every point has equal chance of selection. So that is a uniform probability. Okay. So that uniform distribution is there. Okay. So here we want to test whether the data follows a uniform distribution or not. Again, this data is a summarized data. Summarized in the sense, so 2246 rows, they are summarized. The number of births are summarized according to the season. Okay. Now, how to write the hypothesis? So, if the births are uniformly distributed, so the total number of births, right? If you count the total and divide by 4, because there are 4 seasons. So the number that the probability is 1 by 4, right? The probability is 1 by 4. So we can have probability of the proportion of birth in spring is equal to in summer, in winter, in fall, that is 1 by 4, that is 0.25, right? That means the proportion is uniform. The probability is uniformly distributed, right? So it is uniformly distributed against it is not uniformly distributed, right? Again, the formula is same, right? So here the formula is same, right? Now only the thing is the degrees of freedom is changed now, right? So here this is n minus k minus 1. It depends upon the type of distribution. In uniform distribution, we don't need to estimate any parameter. If there is any parameter, then we can use this k as a number of parameters to be estimated, right? So it is quite a different topic, but just remember, in case of a goodness of fit, we have n minus k minus 1 degrees of freedom. Rest of the procedure is exactly same, right? Now to do this, we can again enter the data. Say for example, in the same file, I can change this as, say for example, spring, okay, then summer, winter and fall. So it is summer, winter and fall, right? And say for example, I want to remove this row, so I can remove the row, right? And here I can change the values. So it is 564, then we have 602, then we have 555, and finally we have 525, right? And you can change the variable name. So this is the season, right? And for the count, you can say a number of birth, right? We can say number of birth in that particular season, right? So this is my data. In the same data file, I am using that, right? Now in this case, let us remove this entire output. Okay. So let us remove this entire output. You can remove that, or you can just change the output, or you can prepare a separate output. Say, let us apply the separate output, separate technique, right? So go to the frequency. Again, it is the chi-square test of goodness of fit. Okay, it is a chi-square test of goodness of fit. Again, this is a season variable, right? And we have the count. So add the count. Now, in this case, what we need to change, right? So look at this. Because we are assuming that the proportion is same for all, right? So totally, if total is 100, then we have 25, 25, 25 and 25, or in short 1 by 4. So that ratio can be taken as 25, 25, 25 and 25. Okay, so this is, and accordingly we have the complete output, right? So this is the output of the chi-square test. If you want expected count, you can add the expected count. So these are the expected probabilities. Now see, because we have assumed that under the null hypothesis, the proportions are same, 1 by 4, 1 by 4, 1 by 4, right? That is 25%. Okay. So in this case, what we have, all the expected frequencies, 561.50, because it is n multiplied by pi. So these are the pi values under the expected, right? And we have the corresponding chi-square test 5.38 test statistics. The p value 0.14. The p value is 0.14, okay, which is not less than 1%, right? So we can say that again, we fail to reject the null hypothesis, and we conclude that the number of birth by seasons are not uniformly distributed, right? So as far as this data is concerned, so the number of birth is not uniformly distributed throughout the season. Okay, so this is how we can use a chi-square test of goodness of fit. Okay, now suppose you want to check some other distribution. So in that case, what we have to do, we have to find out the expected probabilities, and then you can fill up the expected probabilities in this table. Okay, here you can fill up the expected probabilities, right? So this is how we can use a chi-square test of goodness of fit, right? So first we have discussed, 1 minute. Oh, which one? 1 minute. Count is not changed as, just 1 minute. Okay, because uh, because here by default the name is count. Okay, by default the name is count. So that is why in the output it shows the count. Okay, so these are the levels and these are the count. Count means frequency, right? So this is in every case. See, in a previous example also, see here also it is count. Okay, and I have used count, right? But actual label is count. Okay, that is why it shows the count there. Okay, the test value is 0.25. Oh, which test value? It is not, it is under the null hypothesis. See, under the null hypothesis, it is 0.25, right? Because in the hypothesis, we have mentioned that, yeah, because it is equal, uniform, when we say uniformly distributed, right? So look at this. Probability of birth in spring, summer, winter, fall, they all are equal. That is why it is 0.25, right? So how it is different from the previous example? In the previous example, we have different proportion. That is why the name is multiple proportion, right? Here, equal proportion, and it is also known as a uniform distribution. That is why it is a uniform distribution. Okay, so this is a particular case of a multiple proportion, right? It is a particular case of the multiple proportions. Okay, so okay, now let us move to the next, that is mm, the chi-square test of association, which is also known as Pearson chi-square test of association, right? So up to this, we have discussed about one categorical variable, right? In the first example, we have online, offline. Our focus is on the shopping preference. In the second example, our focus is on the grade, right? So in the first example, we have two choices, two levels. In the second example, we have five levels, the grade obtained by the students, right? In the third example, again, we have four levels, the seasons, right? And accordingly, we have tested the proportions, right? Only one variable of interest. In the first example, shopping preference. In the second example, grade, right? In the third example, seasons, number of birth by seasons. So we are interested in that. Now, suppose at a time we want to study the relationship between the two qualitative variables, right? So, see, I use the word relationship. So, when we have two numerical variables, we call it as a correlation, right? When we have two qualitative variable, we call it as association. So that is the difference between the correlation and association. The purpose is same. In correlation, we want to find whether the two variables are related, right? When we say that they are related, that means one variable depends on the other. That is why they are related. In association, are the two variables associated? That means, is there any dependency? Only the difference is association is used for the qualitative variable and correlation is used for the numerical variables, right? So even in that case also, the correlation, we have the formula Carl Pearson coefficient of correlation and this test of association, chi-square test of association. So that is also given by Carl Pearson. So it is a Pearson's chi-square test of association, right? Now let us go consider the same example, right? So what is that example? So we have two variables. One is the shopping preference and another is the gender. So shopping preference has two levels, gender has two levels. So I want to study the relationship between the two levels, right? That means whether shopping preference depends on gender or not, right? In short, whether the male prefer more online shopping or female prefer more online shopping, right? That means, is there any dependency? So that we want to, or what we call it as a association. Are the two variable associated? If they are associated, means the shopping preference depends on the gender. If they are not associated, means shopping preference does not depends on the gender, right? So two attributes. Attributes means attributes is a word for the qualitative data, right? Either nominal or ordinal. A and B are said to be associated if they are not independent. If they are dependent, they are associated, right? If they are dependent, they are associated, right? Are said to be associated if they are not independent. When they are independent, they are not associated. Where they are dependent, they are associated. It is a simple language, right? But they are related in some way or other way, right? So according to Yules and Kendall, two attributes are associated only if they appear together in a greater number of cases, right? So that means greater number of cases is to be expected, right? So if they are associated, so say for example, so male prefer online shopping majority. So if majority of the male prefer online shopping, right, and female, so there is a less number, so accordingly we can define, right? So whether they are associated or not. Okay, so in this case we use the uh, Pearson chi-square test, right? That is used for testing the significance of the association, right? Now remember, in correlation also, we try to find whether there exists a correlation or not, right? So that gives you the strength of the relationship. But this chi-square test of association, it is not giving you the strength of the association, but it is giving you the test. It tests the significance of the association, whether two variables are significantly associated or not. So that can be tested using chi-square test. It is also referred as a chi-square test of independence. Okay, and it is very simple and straightforward procedure, right? So for this, the assumptions are the variable should be either nominal or ordinal, right? And there should be two or more independent groups of interest, right? So either you can use nominal or ordinal variable, and at least two variables are required, two or more group, right? So in that case, we can use this, right? So for a 2 by 2 table, like in our case, this is our 2 by 2 table, two labels for shopping preference, two labels for gender. Okay, so for 2 by 2 table, we have chi-square should not be used if any of the expected frequencies is less than 5, right? So these are the observed frequencies 85, 45, right? When we calculate the expected frequencies, if any of the expected frequency is less than 5, then this chi-square test should not be used. In that case, we have to apply the Yates correction, right? So that is a theoretical topic. Okay, so we can use Yates correction. For larger than 2 by 2, so we have certain rules. So chi-square should not be used if any of the expected frequency is less than 1 or more than 25% of the expected frequencies are less than 5, right? So if more than 25%, 20% of the expected frequencies are less than 5, so this particular technique is not applicable. Okay. Now to understand this, right? So see, as I told you, so this is a raw data, right? This is a raw data. So gender, shopping preference. Okay, so actual raw data we have, right? In earlier two examples, we have used a summarized data, count data, right? So same example we are using, right? So test whether shopping preference is independent of gender, or what we can say, shopping preference, whether shopping preference depends on gender or whether it is independent of gender, that we want to test, right? Now under this situation, your null hypothesis, this is the table, frequency table, right? So this is a some actual raw data. When you prepare a frequencies, you get this type of table. Okay, so you get this type of table. Now, the null hypothesis. So always we assume that there is no association between shopping preference and gender, right? So this is the null hypothesis always, because when we assume that there is association, so we are there is a bias, right? To avoid bias, always we assume that there is no association between the two variables, or we can say that two variables are independent of each other, right? Independent of each other. Or we can say that whatever the observed difference is, observed association is there, that is due to chance. Against, there is an association between the two variable, right? So now since I have a two-way table, this is a two-way table. So this is a row R1, R2, that is row 1, row 2, column 1, column 2. So this 85 is in the first row and first column, right? So we have two-way table. So we can use a formula like this, OIJ, that is observed frequency for the ith row and jth column. Say, for example, this 85 is the observed frequency for the first row and first column, and so on. So we have, these are the observed frequency. Formula is exactly same, only the difference is in earlier example, we use single summation. Here we have to use double summation because we have row wise and column wise, right? And it follows a chi-square distribution with r minus 1 into c minus 1 degrees of freedom, where r is the number of rows, c is the number of columns, and we have the expected frequency, right? Again, expected frequencies can be calculated in a different way, right? Say, for example, in this case, right? Suppose this is the observed frequency 85. I want to compute under the null hypothesis. There is no association. Under the null hypothesis, what is the expected frequency here? So the row total 130 multiplied by the column total 110 divided by the grand total. So it is 130 multiplied by 110 divided by 250. That gives you the expected frequency E11. 85 is E011 observed and expected, right? So that is how we calculate the expected frequency, right? Now, how to do this in Jamovi? Okay, so to do this in Jamovi, first we need to open the data, right? So again, we have the shopping data, same shopping data I'm using, shopping preference, right? Again, go to a frequency, right? Go to a frequency, and we have an independent sample, or it is also known as the chi-square test of association. Chi-square test of association, right? Now remember, if same data we have in a summarized form, then we can use this count option. Now, in this case, we don't have a summarized data, we have a raw data. Okay, we have a raw data, right? So that is why we directly use this, right? So in this case, what we have to do? So we have to use these options, independent sample test, and then select the variables, gender first, and then, so this is the gender, row wise, and then shopping preference column wise, right? Count is not useful here because we are using a raw data. Okay, we are using a raw data, so count is not used here. If the same data is in the summarized format, then we can use count. Okay, so this is a chi-square table. See, actually in my case, our data is a raw data, so it will count, it will prepare a contingency table, cross tabulation. Okay, and accordingly it will compute all the values. Even here we can use the statistics also. So we have a chi-square test. Okay, not that, but we have a sales, right? Expected sales. So see, expected count, we can count the expected values also, right? From here We can count the expected. If you want percentages, so you can use the percentages also. Row percentage, we can use the column percentage also. So we will get complete table, right? So as per your requirement, you can compute all these values. Okay, you can compute all these values. Okay, so this is how we get the output, right? And then we have the p-value, right? Look at the output. So this is the test statistics, right? The p-value which is less than 0.05. It is very, very smaller, right? So it is less than 0.05. So we conclude that there was a significant association between gender and shopping preference. It suggests that shopping preference depends on gender of the respondent. Okay, shopping preference depends on the gender of the respondent. And if you want to report this in research article, so there is a specific American Standard Association, right? American Journal of Association. So accordingly, we can report these values, right? APA style, right? So this is how we can write, right? And we can take the decision, right? So this is how we can use the chi-square test of association. Okay, so it is used for testing the significance of the association and not the strength of the association, right? Now the question is how to measure the strength of the association. Okay, how to measure the strength of the association, right? So measure the strength of the association, we have different formulas, right? So for two nominal variables, we can compute contingency coefficient, we can compute phi coefficient, or we can compute Kramer's V coefficient, right? There are some limitations for each of the coefficient. The phi coefficient of association is defined as this formula: phi equal to under root of chi-square upon n, where this chi-square is the Pearson chi-square test statistics, n is the total number of observations, right? So phi coefficient, it measures the association between two nominal variables. Same type of association is there in SPSS also, but in a different way, right? So it is used for only 2 by 2 table. For more than 2 by 2, it is not that much useful. It is based on the chi-square test. The range of this is always between 0 to 1, right? The phi value is between 0 to 1. The another one, that is the chi-square test contingency coefficient, right? So again, it is used for two nominal variables, but it is an adjustment to the phi coefficient when you have the table which is larger than 2 by 2. Say I have 2 by 3 table or 3 by 3 table, 3 rows and 3 columns. That means 3 level for one variable, 3 level for another variable. So it is a 3 by 3 table, right? So this contingency coefficient is used as an adjustment to phi coefficient for the larger than 2 by 2 table, right? Again, it is based on the chi-square. Its value is ranging from 0 to 1, but the limitation is it never attains the value 0. The formula is under root chi-square upon n plus chi-square, right? This is just an adjustment to the phi coefficient, right? Next one, that is a Kramer V coefficient, right? So again, this Kramer V coefficient, it is used for more than 2 by 2 table. If we have 3 by 3, 3 by 2, 3 by 4, so for that we can use this, right? For two nominal variables. Again, it is based on the chi-square, and the limitation of contingency coefficient, it never attains the value 1, right? Actually, theoretically, it is between 0 to 1, but in actual data, it never attains the value 1, even though there is a strong association. Okay, so that limitation can be overcome by Kramer V coefficient. It can attain the value 1. It depends upon chi-square, n, the number of rows, the number of columns, and minimum of these two. So just compute that and you will get the under root of that value gives you the Kramer V coefficient. Okay, so this is the interpretation, right? Contingency coefficient, phi coefficient, or Kramer V coefficient all ranges from 0 to 1, right? 0, if the coefficient value is 0, means there is no association. If it is very close to 0, there is no association. If it is very close to 1, represents high degree of association, or what we call it as a strong association. Okay, strong or high degree of association. Now, how to find these values? Okay, so if you look at the output, this output, right, for the shopping preference, right? So look at this. Here we have all these because my both variables, gender, male, female, shopping preference, male, female, shopping preference, online, offline. So both are nominal variables. So it is clearly mentioned in Jamovi, right, that this contingency coefficient is for nominal, gamma coefficient is for ordinal type data. Phi and Kramer V are for nominal, Kendall, Toe, Mental, Hazel, that is for the ordinal type data. Okay, so when you select this, so in the output, it gives you additional values. Look at this, it is 0.40, 0.44, 0.44, right? So it shows that there is a association, right? 0 to 1, it is close to 0, no association, close to 1, strong association, and it is mediocre, that is moderate, because it is close to 0.5. So we can say that there is a moderate association between the shopping preference and gender. Okay, so this is very interesting. In Jamovi, it is clearly mentioned. For nominal, we can choose this. For ordinal, we can choose this formulas, right? So that is the important aspect, important point in Jamovi. Okay, so this is how we can use the measure of association for the nominal type data, and we can accordingly interpret that there is a moderate association between the gender and the shopping preference. Okay, so this is for the nominal type data. You can choose the expected value, you can compute. Again, another important point in Jamovi, we have this plot section is there, right? So if you minimize this, so in the plot, so you can choose the bar plot for the same data. So look at this, you will get directly the bar plot. Okay, multiple bar plot, because we are using two categorical variable, shopping preference and gender. So accordingly, it shows you, it gives you the multiple bar chart. Okay, we can have a multiple bar chart, or you can choose either stack. So this is a stack bar chart. Okay, so there are options available. Okay, there are options available, you can choose that, or even you can choose the percentage here, so it will be converted to percentage, right? So even side by side, it gives you the percentage. If you want count, so it gives you the count. Okay, so this is the beauty of the Jamovi, which is not possible in SPSS. So here your output is dynamic output, and you can change that anytime, right? Suppose I don't want bar chart, I want bar chart, I want percentages, so accordingly it will reflect. Okay, so this is how we can use this. Now the next topic, that is about the ordinal data, right? So up to this we have discussed the nominal type data. So for nominal type data, we have the chi-square test of association, we have chi-square, we have the measures of association, right? Kramer V, phi coefficient, contingency coefficient. So these are the measures of association. So in case of the ordinal data, we have some different association measures, right? So for two ordinal data, for two ordinal variables, we can have gamma coefficient. right? We can have a gamma coefficient. We can have a Kendall-Stowe B coefficient, right? Kendall-Stowe coefficient, or we can have a Spearman's rank correlation coefficient, right? So these are used when we have ordinal type data. Okay. Now, what is the formula for that? So look at this. If I have the data like this, so income, right? Low income, high income, and the respondent, whether that respondent is satisfied with the tax policy. So we have not satisfied and satisfied, right? So if one of the variable is ordinal, we can go for a gamma coefficient, right? So this is the table. Okay, low, high, not satisfied, satisfied. Okay, and if we denote the values by A, B, C, D, and total the column, total the rows, and the grand total. So we have this table, right? And then the formula for the gamma coefficient is, it is very simple formula, diagonal AD minus BC. So that is your numerator, right? And then we have the same thing with the addition, right? The difference and addition. So this quantity is known as NS minus ND. What is that NS? So NS is the total number of the total number of pairs of cases rank in the same order. So look at this, low and not satisfied. So that is same. That is also known as a similarity and dissimilarity. Similarity means low and not satisfied, similar, high and satisfied, say similar, right? Now when we call about this B, so it is low income and satisfied, so cross, right? So that is known as a discordant pair, different order. Okay, so this is how we can calculate the gamma coefficient, and the range of this is always between -1 to +1, and accordingly we can interpret, right? Now to understand this, let us take the same example. Suppose I have, this is a raw data, okay, and this data actually it is not up to 7, but there are more, right? Suppose there are 100 such a rows, right? And if the data is tabulated, I am getting this type of table. Okay, so these all red are called similar pairs. Why they are called similar pairs? Because high and satisfied. Okay, high satisfied, high satisfied, high satisfied, low not satisfied, right? So look at this diagonal values, right? So this A and this D, right? So any respondent who belongs to this particular cell and this particular cell, so they are similar pair and opposite, right? That means, say for example, high but not satisfied, right? That is, so these values, high but not satisfied, these 44 individuals, and then low but satisfied 29 individuals, they are known as a dissimilar pair. In other words, they are also known as concordant pairs and discordant pair, right? They are known as concordant and discordant pair. And the calculation is very simple, as we have seen in this formula. So this is how we can calculate, right? And depending upon the value of G, we can interpret, right? So if it is 0, no association, +1, perfect positive, -1, perfect negative. In other cases, we can say that moderate positive, moderate negative, or partial positive, partial negative association. But remember, it is applicable only for ordinal type data. Okay, it is applicable only for the ordinal type data, right? Now, say for example, the same table we are using. Now, see, as I told you, uh, in this case, we have a raw data. Okay, two variables, two nominal variables, and we have a raw data. Look at this. This is my raw data. Okay, one column gender, another column shopping preference, right? And the summarized table. So if I don't have a raw data and I have only this summarized table, then also I can use Jamovi for the chi-square calculations, right? So for that is why I have taken this in the second example, I have taken the count type data. Okay, I have taken this count type data. So look at this, right? Suppose this is the data. I don't actually 100 respondents we have and two variable, income and whether satisfied with tax policy or not. So two variables and 100 respondents. So 100 rows data I required. But suppose I don't have raw data. So what I can do, I can create all possible labels. Okay. Say for example, income, right? So look at this. Income, low income and not satisfied, there are 10. Low income and satisfied, there are 29. So what I can do, I can create income in the two cell. I can use low and here not satisfied, satisfied. So first pair, low and not satisfied 10, low and satisfied 29. Same way, high and not satisfied, high and satisfied, right? And then we can use separate column as a count or value, right? So you can use any variable, any name here, but actually it is a frequency. So count. So instead of raw data, if we have a summarized data, then also we can compute in Jamovi. Okay. So see how to do this. So what we want to do, we want to apply the chi-square test of independence or association, right? So whether, so actually the question is there any association between the level of income and satisfaction with the tax policy? Now remember, earlier we have discussed the coefficient. So coefficient gives you the strength of the association. Okay, we will calculate that also. But actually what we want to test here, we want to test the hypothesis, whether there is any association between the level of income and the satisfaction with the tax policy. So what we can do, we can write the hypothesis. What is the hypothesis here? So there is no association between the two variables, right? And then we can create the table, data table, right? And then we can go for the frequencies, then chi-square test of independence, select income as a first variable, tax policy as a second variable, and count value as a count variable because I have a summarized data. Okay, we have a summarized data, right? And then you will get the chi-square output, right? And then we can choose the ordinal gamma coefficient also. This is the gamma coefficient. So it gives you the gamma coefficient value minus 0.76, right? Minus 0.76. As we have discussed, the gamma value ranging from -1 to +1. If it is closer to -1, strong negative association. If it is closer to +1, strong positive association, right? So first of all, to test the hypothesis, right? To test the hypothesis, look at this. Chi-square value is 20. The p value is less than 0.001, right? So what it shows, less than 5%, right? So there is a less than 5% means reject the null hypothesis. What is null hypothesis? There is no association. That is your null hypothesis. So that is rejected. Means there is a association between the income level and the satisfaction with the tax policy. But what is the kind of association? So its value is minus 0.76, right? Minus 0.76. So there is a negative association between the income level of an individual and satisfaction with the tax policy. Satisfaction with the tax policy. Okay. So this is how we can interpret. Okay. And then accordingly, we can prepare a bar chart also, right? This is a bar chart. You can use the percentage. And if we say within rows, so it gives you the percentage stacked bar chart. It gives you the percentage stacked bar chart. Okay. So we can have a percentage stack bar chart also. Okay, so depending upon the purpose, right? Another formula, that is Kendall tau correlation, measure of correlation, or what is called it as a association, right? And then generally it is used for the ordinal data or rank type of variable. When we have rank data, we can use Kendall tau also, right? We have rank data, we can use Kendall tau, or we can use the Spearman's rank correlation coefficient, right? So this is the formula just for the reference, right? And we can compute. Similarly, we have Kendall tau C also, which is a non-parametric measure of ordinal variable. It is not there in Jamovi, but this is the formula for that, right? So this is all about the chi-square test of association, right? Now, if you have any question regarding the chi-square test, any doubt, right? So this is, see, basically in any research, whenever we conduct a survey, so majority of the times our variables are nominal. It may be a Likert scaling data, it may be agreement, it may be frequency scale data, right? So whenever we have a qualitative data, so there is a big issue about the statistical analysis. So always we go for this type of analysis for such a data. Now, if you have any questions, so you can ask me. Yes, we can calculate Spearman's rank correlation using Jamovi also. It is there in the correlation section, right? Because we are discussing the frequencies, and frequencies are used for the qualitative data, right? And when we have numeric data, so for numeric data, we have Carl Pearson measure, we have Spearman's measure, so we can use that in that section. So I think it is the last session, correlation and regression. So sir will discuss about that. Okay, anyone? Any other question? Is the content useful for you? Exactly same way for the Likert scale, right? So actually, whatever the data we have considered, that is what we call it as a nominal data, right? Or ordinal data. Okay. So in the Likert scale, what we have agreement type, strongly disagree, disagree, neutral, then agree, and strongly agree, right? So it is a Likert scaling data. So exactly same way you can apply all these techniques in the Likert scale also. Thank you. I hope you find it useful in your research or in your analysis.
If you want to speak, you can unmute yourself and
You
speak.
can unmute yourself. Exactly, you need to practice. And initially also I told you that because it is online workshop, right? So in online it is very difficult to conduct hands-on training. So when we conduct offline workshop, so one-to-one, it is just like one-to-one, right? So in that case, it is possible to do hands-on training also, right? But we have prepared the presentation in such a way that by referring the presentation, you can do yourself on your data.
Okay, thank you, sir. We extend our deepest gratitude to you, sir, for your exemplary guidance and expertise during the enlightening session on chi-square test of association and goodness of faith. Sir, your
Thank you.
clarity in
Yes, madam.
Sir, your clarity in explaining intricate statistical methods coupled with their patient manner made the complex concepts accessible and comprehensible to all participants. We're immensely grateful to you for your valuable contributions, which have undoubtedly enriched our understanding of statistical methodologies and their applications and in research and decision making. Thank you so much, sir, for your session.
Thank
We
you,
will
madam.
meet on Tuesday, sir. Again.
Yeah. On 22nd, na?
Yes, sir.
Yeah. And for the reference book, so actually there is no specific reference book, but at the end of, I think my last slide, it contains one link. You can go to that, go through that link, and you will get. Yeah, obviously, your presentation for obviously, we always share our presentation data set, right? So that user can refer it anytime, right? We never keep all these presentation with us, right? Because it is, uh, if someone is using it for the research or for understanding, right? So it is always better to share everything. Okay. So we always share the presentation. Not only presentation, we always share the data file also.
Okay, sir. Whatever you share, I share to them. I have sent
Yeah.
through mail. Yesterday's videos alone is yet to be sent today.
Okay. Okay. Thank you very much.
Thank you so much, sir.
And good night to all.
Good night. And Noor, you have given your official mail, and so that you could not receive the mail what we are sending, there should be a Gmail account for to receive your documents, etc., or certificates, etc. Noor, can you get me? Whatever we are sending is not dispatched to you. So please join.
I shared my email ID on the chat.
Okay, you mail us, please. No, this mail ID will not is not working because Gmail is not sending messages to this kind of official mails. You please come with your Gmail. Okay, whatever we are sending is not dispatched to you. It is coming back to us.
Hello, ma'am. Hello, ma'am.
Yes, Kanchana.
Yes, ma'am. Kanchana here. Ma'am, please, ma'am. Maybe I make a mistake in sending it to the Yahoo mail. Please,
Yes,
can you
send
share for
again.
me?
We will send
From the
again.
first day, ma'am. From the first day, because you know, ma'am, I'm a research student from College
I
of
will
Nursing.
send you all
I want to
the.
practice the analysis, ma'am. Please, can you share for
Tomorrow
me, ma'am?
morning we will be sending. Okay.
Okay, from the first day onwards, ma'am. Thank you, ma'am.
Thank you.
Thank you. Thank you so much. Thank you so much.
So participants, please kindly note that you should come and log in only with your Gmail or register only through Gmail account so that all the files will be easily shared to you. Don't come or log in with your other official accounts like ac.in, etc. Those email IDs are not working with Gmail. Okay. Thank you so much. We will meet on Monday again. Thank you.